Welcome to another episode of Quintus Technologies Tech Talks. I'm Chad Beamer, Applications Engineer for Quintus Technologies, and today we'll be interviewing Jeremy Iden, CTO of Elementum 3D. Jeremy, can you introduce yourself and tell us a little bit about Elementum 3D?
Hi Chad, thanks for having me here. So I have a PhD in materials science from the Colorado School of Mines, and I have over 20 years of industry experience in materials research, development, with a focus on powder metallurgy, reaction synthesis, metal matrix composites, and additive manufacturing. So Elementum 3D was founded in 2014 with a mission to expand the materials library available for additive manufacturing. We're based in Erie, Colorado, and have in-house printing and powder feedstock production. Today we have 50 employees and 22,000 square feet of facility space, but are looking to expand. Many of our materials use patented reactive additive manufacturing, or RAM technology, to produce improved properties compared to other AM options and even compared to similar Wrought alloys. We're most known for our family of printable aerospace-grade aluminum alloys, but also offer printable coppers, refractory metals, and are working on introducing a whole family of printable high-performance nickel alloys.
Very exciting. Jeremy, can you give us a little bit more detail about your reactive additive manufacturing material system and what that means to AM?
Reactive additive manufacturing is reaction synthesis inspired, where we're using precursor phases to form product phases in situ during the AM process. And so these in situ formed product phases really provide a lot of great benefits, including dispersion strengthening to improve the properties of the material, but they can also serve as inoculant sites to heterogeneously nucleate the grain structure of these materials, leading to a more equiaxed, fine-grained microstructure with improved properties, including solving a lot of the printability challenges that the traditional materials might face.
Very interesting. And for a little clarification, is this approach more geared towards innovative new materials for powder bed fusion approaches, or for traditionally manufactured materials with slight tweaks to their existing chemistry?
Great question, and it's actually really well suited for both of those things. We can take traditional materials that were designed for other traditional processing, like Wrought processing, that may not have great weldability or printability in the laser powder bed fusion type AM processes, and we can modify those alloys with fairly small compositional changes and now make those versions printable with great microstructures where otherwise they would suffer from extensive cracking. But beyond that, we can also make brand new alloys, including metal ceramic composites with high performance that exceeds both what's available for additive manufacturing today, but also traditional Wrought alloys with improved strength, modulus, high temperature performance, wear resistance, and even reduced coefficient of thermal expansion and other exciting properties, including great high cycle fatigue performance.
Well, it sounds like you're going to have plenty of opportunity with your RAM technology. We're meeting today to discuss a little bit about nickel-based alloys specifically. So let's transition a little bit. Can you speak about the general interest in nickel-based superalloys for AM, specifically the aerospace industry?
Superalloys are a great fit for AM, and that's really because they're the preferred material for high temperature strength, creep resistance, where you also need good corrosion and oxidation resistance. The Gamma Prime family of nickel superalloys, they really offer the best creep performance at high temperature combined with that oxidation and corrosion resistance. And many applications like turbine blades are well suited for AM because of opportunities to improve cooling efficiency and therefore overall efficiency, and also because legacy production methods are very specialized and the production volumes are addressable by AM.
So we know there's always trade-offs. Jeremy, can you speak to some of the challenges that these particular material systems present with the additive powder bed fusion approach?
The printability, well, and it's well known actually, even the weldability of the nickel superalloy family varies. There's some that are considered quite weldable, others are either very difficult to weld or even considered non-weldable. One of the biggest factors in the weldability of the material is the fraction of the gamma prime phase content. As you increase in gamma prime phase, the weldability generally drops. Weldability tends to be very applicable to the printability. So a material that has poor weldability is going to have poor printability with laser powder bed fusion as well. So the issue is you try and print these very desirable materials and you get significant cracking throughout the microstructure, and the properties of course suffer. Not only are the higher gamma prime alloys challenging though, some of the even solid solution strengthened alloys such as alloy 230 can also suffer from printability challenges. With these types of solid solution strengthened alloys, one of the problems is that you get very columnar grain growth from one layer to the next, and you can get very long columnar grains that suffer from intergranular cracking during the solidification of these alloys. And so both of these problems make nickel superalloys difficult to address through printing, or at least many of the nickel superalloys.
Yeah, the problems you've highlighted clearly are going to have a negative impact on mechanical performance and reliability, which then is a challenge to be able to introduce them into the aerospace industry. But as we know, where there's challenges, there's opportunities. So what potential solutions are out there to help address these challenges?
There's multiple approaches you can do, and one of the ones that's been traditionally investigating is using hot isostatic pressing to heal up the internal cracking and defects that can develop during printing of these alloys. And there's been a lot of success with this approach. You can heal up most of these internal cracks and provide great performance improvements for these alloys that are susceptible to such defects. Now, there's some challenges with that though too, in that while you can heal up the internal cracks, any surface cracks that are open, those won't benefit from the HIP process. And so you have to deal with those a different way. There's surface treatment approaches. You can use chemical, mechanical polishing, or other types of surface treatments to remove the surface cracks. But one of the ways Elementum's been focusing on dealing with this is through modification of the alloy. So for alloys like the alloy 230 that's suffering from the solidification cracking, we've been able to shift the columnar equiaxed transition curve for that alloy with our RAM process by forming inoculation sites during the solidification process. And so that allows for a more equiaxed, fine-grained microstructure that doesn't suffer from the same solidification cracking problems that the traditional alloy does. And now we found that combined with a Quintus HIP process provides even further performance benefits. With the gamma prime phase fraction alloys, we're also using the RAM process to improve the properties and performance of those alloys and eliminate the cracking there as well.
So really leveraging some advanced technology and unique chemistry approaches to make these materials printable, improve their performance and reliability. You're also taking it a step further with the hot isostatic pressing approach, and that you're investigating the use of high pressure heat treatment in a modern Quintus HIP system, utilizing the uniform rapid cooling and even uniform rapid quenching to get the densification and steer the microstructure. Can you speak a little bit about high pressure heat treatment and what opportunity that creates?
This is really exciting work that we've been doing together with you at Quintus, and we've looked at our Rene 80 RAM 1 alloy, and we found that with the Quintus high pressure and rapid cooling HIP approach, we showed approximately 20% more ultimate tensile strength combined with 160% more elongation than the same material with a traditional HIP process. So that performance improvements, really comparing a traditional HIP to the high pressure and in situ heat treatment approach in the Quintus HIP.
And that was a study performed on Rene 80. I believe you've also investigated other nickel-based superalloys or high gamma prime, gamma double prime alloys. Is that the case? And what have you observed with the mechanical properties in those investigations as well?
We've been working on a number of different gamma prime-based alloys like the Rene 80, but we've seen similar performance improvements even in the solid solution strengthened alloys like alloy 230. with the Quintus hip approach. For our alloy 230 Ram 1 material, with the Quintus hipped approach, high pressure and rapid cooling, we found a 500% increase in elongation compared to the unmodified alloy.
And in that case, you're not sacrificing strength, is that correct?
That's exactly correct. In fact, we've nearly doubled the yield strength at 760 degrees Celsius compared to the even a Wrought alloy of the same alloy 230 composition.
So some very interesting results with mechanical properties. If we take a step back and look at the resulting microstructure, right, the porosity, the defects internal to the material, as well as the grain size, grain morphology, what kind of learnings did you gather there?
I think the microstructure really tells a great story all on its own. When you look at the alloy 230, you see extensive microcracking, vertically oriented in the growth direction. That's from the solidification cracking in that alloy. And with all that microcracking, you can tell that that material, without modification, through the RAM process and without hipping, it's not going to perform well. It's not going to be reliable, especially in fatigue type situations. So we found that both the RAM process, we can eliminate that microcracking and get a huge performance gain on its own. Now, in the AM process, there's going to be inherent defects that are going to be present. There's always going to be some level of porosity, even if it's relatively minimal compared to other casting and so on approaches. But there is still going to be defects on a micro scale through the AM process that are inherent. And that's where we found that even with a crack-free as printed alloy, the Quintus hip approach can really make huge performance improvements. That high pressure process can heal up those internal defects. And now one of the challenges is that with many of these alloys, especially the gamma prime type alloys, you need to follow up that hip approach with a traditional heat treatment. The traditional heat treatment at those high temperatures can open those pores right back up after you've healed them with the hip. Now with the Quintus approach, you can do both the hot isostatic pressing for healing up those pores. You can combine that now with the solution treatment and the aging that's needed for those alloys to get the right properties because of the rapid cooling that the Quintus systems allow. So that full in situ heat treatment and hip approach, we found that there's significant property improvements here.
And you've even observed some additional benefits with your RAM approach to these material systems with respect to creating an equiax microstructure or enabling that. Can you speak to that a little bit?
So the RAM approach, as mentioned, there's a number of things that can do. But one of those is it can provide inoculation sites that nucleate the grain growth of these alloys during solidification. That can form a relatively fine equiax microstructure with more isotropic properties, both in the growth and XY directions. So that's beneficial for predictable uniform properties. And now you can control that microstructure through the subsequent heat treatments as well. And not only that, but the RAM reinforcements can also serve as grain pinning sites, and they can help with other properties and maintaining of performance at temperature as well.
Very exciting. You're kind of laying out a path to truly kind of optimize these materials for mechanical performance. And I'm sure the design community loves to hear some of these approaches. I also find the grain pinning very interesting because when I think of grain pinning, I think of high temperature creep performance. So with that said, what's next with Elementum 3D with these two projects?
More testing. We're going to continue with property testing, and like you mentioned, the creep is going to be a big part of that. So we're going to be doing a lot of creep testing, more fatigue testing, and continuing to collect data to fill out that data set for our customers.
Very, very exciting. So taking it one step further, what kind of impact might this have on AM and the industries it serves?
This is where it gets really exciting because not only is this going to impact AM, but it's going to have big impacts across other industries like power generation and aerospace. AM provides enhanced design capabilities and fabrication capabilities for complex components. You can increase cooling efficiency, engine efficiency, turbine efficiency, those kind of things through AM design, including reliability and robustness by combining multiple parts that maybe needed to be welded together. You can combine those now into one robust part. So all those AM improvements are nice on their own, but they need the right materials to take advantage of them. And the current materials, the materials that were currently available, there are some okay options, and they can address many applications. But unfortunately, many of the really higher performance materials, the gamma prime containing materials, the higher creep resistant materials, they simply weren't printable before, or printable with adequate properties compared to traditional manufacturing. And so you couldn't take advantage of all these capabilities that additive manufacturing offers. And so by combining these high performance materials with additive manufacturing, I think that really opens the door on game-changing technology for these industries and allowing applications that traditionally weren't suitable for additive manufacturing because of lack of materials and processing technology. Now those materials can start to be printed, and we can see these big performance improvements, saving energy, reducing carbon dioxide emissions, and so on.
Jeremy, you showcased a very fascinating product line and fascinating work that is clearly going to have an impact on AM and the industries it serves, especially the findings you presented to date on some of the challenging to print nickel-based superalloys. I know Quintus is very much looking forward to the resulting creep and fatigue testing that you plan on performing, and I'm sure others are as well. Thanks for taking the time to speaking with us today. And Quintus Technologies is very much looking forward to our continued collaborations.
Thanks, Chad. We're really excited about this work too, and we really appreciate the opportunity to work with you and the benefits that we've seen from your high pressure and rapid cooling HIP process. I think this is a great collaboration. I'm really excited about the opportunities that this is going to bring for multiple industries.
Thanks once again, Jeremy.
Thank you.